Hello everyone. Let's look into the next stage of the physical design flow, which is the routing and DRC stage. So routing by itself means that we need to route 2 points. So it says that, for example, you have this D in one, okay, and you have this input of flip-flop 1. D in 1 has to be connected to flip-flop 1, or basically there should be a physical wire between D in 1 and flip-flop 1 to maintain a physical connectivity between these 2 points. But from an algorithmic point of view, the software identifies D in 1 as your source, okay, the flip-flop 1 input pin as a target, and the algorithm has to find the best possible solution to connect between D in 1 and flip-flop 1. Okay, so that's basically is the routing algorithm. So while we discuss route, it's not just connecting between two endpoints, but to find out the best possible connection between two endpoints, with one point being the source and the other point being the target. Okay, so there are various algorithms being developed over the time, and we are going to look into one such algorithm. Let's try to remove the netlist and the power lines from here, and let's look into one such algorithm, which is called as the maze routing, or it's called the Lee's algorithm. So Lee is a very famous person who actually invented this maze routing concept, though it has got some limitations, but he was the first one to start or to come up with algorithms of routing. So when we say routing, it means that we need to connect 2 points. Let's say we have to connect, let's say we'll take an example. If you have to connect these 2 points from point A to point B, so this point A will act as a source, this will act as a target, and you have to find out the best possible path or the shortest possible path to connect A and B with less number of twists and turns. By twist and turns, we mean that there should not be any zigzag, there should not be minimal zigzag lines. Most of them should be L-shaped. There should be very few that should be Z-shaped, and there should be very few lines that will be zigzag shaped. So we are looking for the best possible solution to connect between A and 2. There are various methods to connect point A and point 2, but we are looking for the best algorithm. So from an algorithmic point of view, for the software, it is just two endpoints, and the software has to connect these two points. Basically, there are some search algorithms, there are some kinds of algorithms that it has to run in the backend to understand the best possible route between 1 and 2. But from a physical design engineer point of view, it's a route, it's basically a physical wire. And from an algorithmic point of view, it's basically two different points which has to be connected. Okay, the algorithm doesn't care whether it's a flip-flop or it's a buffer or something of that sort, to some extent. But for what does the algorithm cares about is there are 2 points which we need to connect. So let's look into one such algorithm. We'll remove all the remaining things and keep only this one, because this is again needed, as this acts as a blockage for the routing. So for example, there can't be any route that can go like this and over the top of these blocks and go to the right side. That's not allowed. So we have to take care of this blockage as well, this obstruction as well. For the algorithm, this will be acting as an obstruction. So basically, the coordinates that it sees for this particular set of boxes, the algorithm understands that it can't put any route through this particular obstruction. Okay, let's look into the algorithm now. So for example, you have this as initially what the algorithm does is it creates a grid. It creates a routing grid at the back end with these two as a points that needs to be routed. So this is called as routing grid, and there are some standard numbers for this, or standard dimensions of this grid. We won't get into details of that, but there are some standard dimensions. Okay, we're trying to explain the concept of the Lee's algorithm. So there is a routing grid that is being built at the back side of your floor plan, and it already has, if you try to look into any of the tools and you try to zoom in of those tools, you will able to see these routing grids. Okay, and then when the algorithm makes this routing grid, it creates 2 points. So one is called as the source, and the other one is called as the target. Now through the help of this routing grid, the algorithm has to find out a best possible way to connect this source with this particular target. So how does it do that? So what it does, the first step that the algorithm does is it tries to label all of the grids that is there around it. So the first grid, the adjacent grid that it sees next to its source, there are 4 adjacent grids to this particular source. One is this one is this one is this one, and one is this one. It tries to label these grids called as 1. Okay, so all the adjacent grids, all the not the diagonals one, but which are vertical and horizontal adjacent to the source grid, they are being labeled as 1. Okay, let's do it in this way. Let's try to label all the adjacent one as ones. Okay, now let's take each and every checkboxes for 1. Let's say this particular grid of 1. Now this grid will be this will follow the same procedure. It will label all its adjacent grids as the next number, which is 2. So for this one, the adjacent grids are this one and this one, not the diagonal ones, only the adjacent grids which are horizontal and vertical to it. So so this grid which is adjacent to 1, this grid which is adjacent to 1, and this grid which is adjacent to 1, they will be labeled as the next number. Similarly, let's say we'll take one more, let's say we'll take this, or let's say we'll take this grid, this particular grid box. Okay, so this has 1 and its adjacent grid boxes are this one, this one and this one. So they will be labeled as the next integer, which is 2. Similarly for this one, similarly for this one. Let's do it. Okay, so now each and every ones over here are being the adjacent grids for this grid box 1 has been labeled as the next integer, which is 2. Similarly, it has been happened for this one also, it has been happened for this one and for this one also. Next is we will take this 2, we'll take each grid box which is labeled with 2 and label its adjacent grid with the next integer. So for example, let's say this particular grid box, it is being labeled as 2. The adjacent grid box for this grid box 2 is this one, it's this one and it's this one. So let's try to label it as the next integer. So we'll try to take this, we'll take this particular grid box and its adjacent grid box will be labeled as the next integer, which is 3. Similarly, we'll be doing it for all 2s. For example, for this 2, the adjacent grid box is this one and this one. For this 2, the adjacent grid box is this one and this one. Okay, and not the diagonals one. Diagonals are not the adjacent ones, but they are diagonal. So we're looking for vertical and horizontal adjacent ones. So for example, for this grid box which is labeled as 2, its adjacent grid boxes are this one and this one, and they will be labeled as the next integer, and the next integer over here is 3. So let's see whether we have done it or not. So we'll put a 3 over here. So now if you see any of the 2s, any of this particular 2, all its next adjacent grid box, for example this one and this one, are all labeled as the next integer number. For example, now let's say this 2, it has got 2 adjacent, one is this one and one is this one. This is also an adjacent, but it has already been labeled. So we have to find out the next unlabeled adjacent box to get labeled. Okay, so the next adjacent unlabeled box was this one for this 2, and it has been labeled as 3, and this grid box which is again adjacent to 2 is being now labeled as 3. And you can pick up any of the 2s over here. For example, let's say you pick up this 2 which is pointing over here. The adjacent grid box to it's labeled as 3, and the next adjacent grid box is being labeled as 3. Okay, and the same procedure follows. So so we have to take all the grid boxes which are being labeled as 3, for example this 4, this 4, this 4 and this 4, and take the adjacent grid boxes of it and label it as the next following integer. Okay, so for example, this particular grid box which is now labeled as 3, its adjacent grid boxes which are empty are this one and this one, and all this will be labeled as 4. Okay, so what we'll do is, since we have to do even more resourcing of the, or even more labeling of the grid boxes, and we are already running out of time. Let's try to take this particular algorithm in the next video. Thank you. Hello everyone, let's continue our discussion with the Lee's algorithm. So the next step is to take the grid boxes adjacent to 3 and label it as 4, basically next integer. So we have, let's say we have this particular grid box which is labeled as 3. The adjacent for this particular grid box is this one and this one, and we have to label it as the next integer, which is 4. Similarly, for all 3's, whichever is present on the boundaries, we have to take the next grid box and label it as 4. Let's do that. Okay, and we have to continue doing this till we reach the target pin. Okay, and we have to continue doing this underneath this particular blockage as well, because there is a routing grid which is present inside under this particular obstruction, but the obstruction just specifies that we can't use this route to connect from source to target. So if you see, we are moving close to the target. There are multiple ways to reach to the target, and this is also one of the ways, but this way can't be chosen because there is an obstruction lying over here. Okay, so let's continue doing putting the adjacent grid box of this particular 4 as the next, and label it as the next integer. So for example, in this case, this 4 has got this one and this one as the next adjacent grid box, and let's label it as the next integer, so it's called 5. Okay, so if you see over here, there's one 5 which is underneath this particular blockage, but it's not basically visible because it can't be used, and because of the presence of blockage over here. Okay, similarly you have this 4 which has got this 5 and this 5 and this 5, and for all the 4s which you which was there at the boundaries, there is now a 5 to its adjacent grid box. Okay, next let's move on, and let's continue doing it for 5 also. We have to take the adjacent boxes for grid box 5 and label it as 6. Okay, so all the 5s which was present over here, their adjacent grid boxes are now labeled as 6. Similarly, now we'll take the 6 and label its adjacent grid box as 7. Let's do that. Okay, so the grid box which you see adjacent to 6 are all 7s, and there are some 7s below this also, but it's not visible because of the blockage. If you see, there is a small 7 which is visible over here, and the reason is this lies somewhere outside the routing grid. Okay, so you have this 6, the adjacent ones are 7, so this is 7, this is 7. Let's say if you have this 6, the adjacent grid boxes are 7. Okay, and so on. Next we have to take this 7, we have to look into the 7, we have to look into the grid box with the label as 7, and label the adjacent grid box as the next integer, and that is 8. Okay, so we have taken all the 7s, and over here if you see, there is a limitation. We can't go inside this area because this is again a logical blockage. Remember, in the first video we had, in the first section, we have added this particular logical blockage so that there is no logical cell or routing coming into this area, because this area is being reserved for pins. So that's why we had put a logical blockage, a placement blockage over here. Okay, moving on, we have this 8 which is coming in adjacent to 7. For example, if you see this particular grid box with a number 7, it has got the adjacent grid boxes labeled as 8. Okay, next let's move on. Now we have the next integer as 9, and now we have actually hit the target. Okay, so if you see, from source to target, there is a path to reach from source to target with the help of this numbering. And how does the algorithm does so? It will trace some path. For example, if you have this S, if you have this T, and let's try to move in some direction. For example, if you take 1 2 3 4 5 6 7 8 9 and then the target, so this forms one of the way. There is one more way that gets formed, something like this. If you have this as your source and you have this as your target, there is another way. For example, this one, there could be 0 1, or for example, let's look into the grid boxes first. So if you have source over here, you have 1 2 3 4 5 6 7 8 9 and the target. So this is one way to reach the target. Or you can take this 1 2 3 4 5 6 7 8 9 and then the target. You can take this zigzag fashion. For example, the route will look something like this. Okay, there is another option that you can do is, let's look into some more options. For example, now if you have this as your source and if you have this as your target, you can even take this route, 1 2 3 4 5 6 7 8 9 and the target. Okay, so you can even take this route, and now we have to identify which one should we be picking up. So the difference between this one and this one is that this one has got too many zigzags. It has got two bends, one bend which is over here and the second bend which is over here. Okay, and the other one has got only single bend. So any route with single bends are mostly preferred in case of a routing algorithm. Okay, so for example, in this case, if there are scenarios where there are no other options, this would be preferred. But since there is an option available of an L-shaped routing, this is being mostly preferred by a routing engine or any routing algorithm. Okay, so this is one of the routes that this block takes to this particular block, and this maze algorithm is being used for global routing. There are some limitations to this. For example, if you see, it creates a maze first, then it starts numbering from source, then it moves to target. So for one route was fairly simple, but if we have like millions of routes, this method tends to consume lot amount of time and memory. Okay, because it has to store all the information. Whichever is the best route, it has to store all the information. It has to store the routing grid information, and it has to finally trace a path from source to target, whichever is available. So this is basically a time consuming, and this takes a lot of memory, and there are options to solve the problem of runtime and memory. There are some other algorithms like line search algorithm or Steiner tree algorithm. So there are other algorithms available for in replacement to Lee's algorithm, but they follow the same method. Basically, they work on the shortest routing principle. they're looking for a shortest routing path from source to target. They all work on the same principle. Okay, so let's take another example. For example, we have to connect this flip-flop 1 to this particular one. So what we'll do, we'll follow the same process. Let's remove all of them and keep the blockage only. So we'll first of all prepare a grid for it. We'll use the same grid that we used in the for the previous example. We'll have one source and the target, and the numbering for the maze. Okay, so let's say these are the numbers we have just we have now, since we know the maze, since we now know how the maze is getting created, we have just put the maze numbers over here. We have labeled the grids as per the rules that we, or as per the algorithm that we used in some time back. Okay, so you have now this particular source, you have this particular target, and we have to find the best possible route to connect source and target. So there could be one way. Let's say you have this 1 2 3 4 5 6 7 8 9, or 6 7 8 9, something like this. Or you can use a straight line, for example 1 2 3 4 5 6 7 8 9, and then the target. You can use this route as well. Okay, so this one, the normal route has got one zigzag, or basically there are two bends over here, and there is one more option possible which has got only a single bend, which goes something like this. And again, this is the most preferred way to route the source and the target, since it has got only a single bend, whereas the other one that we just showed has got two bends. One comes from here and one is over here. So usually it is always preferred to have routes with lower number of bends. Okay, so that's the reason we prefer having this one. The algorithm prefers having this one. So that was about a route. That was the basic routing algorithm, and we will be having a whole set of videos for that covers only the algorithm. So if you actually look into the algorithm that we just discussed, it was about connecting 2 points with the shortest route possible. That was the whole aim of routing. So routing is a step for the physical design engineers, but actually if you see, it's algorithmic problem that we need to solve, and for that we need to know basics of algorithm. So we'll be trying to cover a complete video, a complete set of videos on algorithms, not over here, because the purpose of this video lectures is to cover the physical design flow or physical design stages, and routing is one of them. So this is one of the algorithms that we just discussed. Moving on, what we'll be doing is we'll be routing all of them in some fashion. So if you see, we had routed from 1 to 2, and we have routed flip-flop 1 to flip-flop 1 to this particular logic cell 1. We have explained the algorithm for this route and for this route, and similarly similar algorithms will be used and applied for the remaining routes, whichever we need to route over here. Okay, so that was about route and the routing algorithms, and it's very important to know the basics of algorithm and basics of routing algorithm, so that will help us to build the complete algorithm class. Okay, next is to DRC clean. So while we do routing, it's not just about connecting 2 points. We need to look into certain rules that we need to follow while routing. So what we'll do, since I'm already running a bit late out of time, we have already discussed the routing problem. Now we'll try to identify the issues while routing, and we'll try to solve those problems and the things that we need to take care while using an algorithm like maze algorithm. So let's try to look into all those from a DRC perspective in the next video. Thank you. Hello everyone, let's look into few of the rules that we need to follow while doing a proper routing. So it's called design rule check. It's the short form is DRC. So while we do it, what we'll do, we'll take some example we'll take some handful of examples of DRC and try to see how do we do it. So for example, let's say this particular section of the circuitry, you have these two wires which has being just expanded over here. So the rule says that whenever you try to build two wires, there should be a minimum distance between these two wires, and there should be minimum spacing and all those things. So let's try to look into few handful of rules while trying to route these two wires. For example, we are trying to connect this buffer with this buffer and this flip-flop with this logic gate 1. So while doing that, we see some parallel routes, and there should be certain rules that we should be following while following any kind of routing algorithms. Okay, so let's try to look into few of them. So for example, the three basic rules for this below pair of wires will be: the minimum width of the wire should be some X number. So this is the minimum wire width, and the rule says that the width of this particular wire should be some at least this much. It can be greater than this much, but it should be at least this amount. So what it says is basically there are some techniques to build these wires, and those techniques are referred to as photolithography, optical photolithography techniques. And these techniques use light to build these wires, and light has got certain minimum wavelength, and with that particular wavelength it can draw a certain minimum width of the wire. Okay, so considering that into mind, we come up with this certain rules, and the rules say that the optical wavelength of the light is so small that the wire width, the minimum width of the wire should be at least this much. You can't go below this one because it can't be printed. Okay, that's what the rule says. It's basically mostly related to the optical lithography techniques, and we will be talking a lot about optical lithography in a separate videos, in a separate section, where the lithography as well as the DRC rules will be in junction with each other. They will be in par, they will be going hand in hand. Okay, in this case let's try to understand a light. This all wires that you see that are built with the help of some light, and light has got certain wavelength, and that wavelength of light can build a wire with certain minimum width. Okay, it needs, the wire width will be at least this much. It can exceed this particular wire width, and in most of the cases it does exceed. Basically the shape that you see of the wire over here, it's not always rectangle. Once it comes after lithography, there will be some vibrations over here. Okay, so those things will be talking in a separate set. But right now the optical wavelength of the wire says us that at least the wire width should be this much. You can this it can be more than this, but it can't be less than this. Okay, there's another rule that the lithography thing tells to us, is that the minimum pitch between two wires should be this much. It basically says that the center to center distance of these two wires should be at least this much. So these things comes after a lot of optimization done on the lithography system itself. So there are multiple lines that are getting printed. So how do they come up with this wire pitch? So they print multiple lines with varying pitches, starting from closest to the widest, and then they come with an optimum numbers, for example this one, which will be printed very faithfully. So what you see on the mask is what you see on the silicon. That's how they come up with these particular numbers. Okay, and we'll be talking about more of optimization on lithography techniques in a separate set. Let's try to focus on the concepts over here. So this is how they come up with this minimum wire pitch and minimum wire spacing. Okay, there is a third rule. There is one more rule that below two pair of wires has to follow, and that is the wire spacing. So it says that minimum spacing between these two wires should be at least this much. It can't be less than this. It can be more than this, but it can't be less than this, because it won't be getting printed on a silicon as per the optical lithography rules. Okay, so these were some few basic DRC rules, and there are thousands of rules that the router need to take care while routing between two logic cells. While routing all these nets, the router has to, or the routing algorithm has to be aware of at least 1,000 rules. We have just mentioned 3 of it. Okay, and this will be more clear and more sensible when we try to match this with some lithography courses. So let's try to keep it over there. Let's look into another section. For example, let's say we have this section. This section has got has got two nets. One is this one, which is an orthogonal net, and one is the straight net that is going above it. So the basic problem that you see with this net is that they are shorting. So there is a signal short over here. So this flip-flop is communicating with this particular logic cell, and this buffer is communicating with this flip-flop. In the process, if you see, when this buffer tries to send a signal to flip-flop 2, it gets shorted with this signal, because both are same wires and on the same metal layer. So we need to take care of this kind of situation, and this particular situation is referred to as signal shorts, because your signals are getting disturbed over here, and it's a potential violation in a VLSI world. Okay, so these things might lead to functionality failure and so on. So these are very serious things that we need to be looking for. So the signal short is one of the rules. Apart from that, the remaining 3 rules will be still maintained between these two wires: the wire width, the wire spacing, and the wire pitch. So let's quickly see how do we solve the problem of signal short. What we do is we take this particular layer, or we take any of the layer and put it on a second layer. For example, let's say this colored wire is referred to as metal layer MN, and N is either 1, 2 something. So we take another layer which is MN plus 1, which is metal layer n plus 1. For example, if this was metal 2, let's say for example, if this was metal 2, there will be one more layer that will be introduced at the top of it. It will be called as metal this. If this is metal 2, this will be called as metal 3. Okay, usually the upper metals are wider than the lower metals. We have not shown it over here, but from a DRC point of view, or from a signal integrity point of view, you have the upper metal layers wider than the lower metal layers. Okay, while we use this technique to solve the signal short problem, there are few more DRC rules that come into picture. For example, let's look into few of them. So this, we have solved the problem of signal short, but we have increased the number of DRC check, something like this. So you have two new DRC rules that needs to be checked. One is the via width. So you need to connect the bottom metal layer to the top metal layer, and that you will be doing through with the help of a wire. It's like a screw that you try to connect between two different things. Okay, so this is the via, and the rule specifies that the via width should be some minimum value. It can't go below this, but it can be more than this. But for a via which is something like this, it specifies the via width should be some number, and it can't be less than this. And this again related to the optical lithography technique. So most of the rules that comes of all of the rules that comes, the design rule checks that comes from the optical lithography point of view, the lithography techniques point of view. So it's very important to understand what lithography technique is, and how do these numbers are extracted from the lithography experiments that we do. Okay, so based on the lithography experiments, so one of the experiments that we can share it right over here is they print the square boxes that you see. They print these square boxes multiple times at varying widths, and then they come up with a width saying that this is the minimum width that can be printed by an optical light. Okay, and there is one more rule that comes, is the wire spacing. So minimum spacing between these two wires should be at least this much. It can be more than it, but it can't be less than this, else it can't be printed. Okay, so it's more of a printing. How do we print what we see on the layout, and that's what a layout term comes into picture. So this has to be laid out onto a silicon, and that is done using lithography techniques, and those techniques come up with some rules with which the algorithm, the routing algorithm, needs to follow. Okay, so we have covered the DRC technique in brief, and there are like tons of DRCs that we need to learn and understand, and that will be binded with the lithography lectures that we'll be uploading in some time from now. The next step is called as parasitic extraction. So basically, whatever wires you see over here, these wires are nothing but some physical wires. They have got certain width and height, and the resistance and capacitance of this particular wires needs to be extracted and to be used for some purpose, something like this. So if you see the resistance and capacitances on this particular wire, each and every wire has got some finite value of resistance and capacitance, and this needs to be extracted and used for further process. Okay, so since I'm already running out of time, what we'll do, we'll see how do we extract the parasitic. We'll look into certain formats, it's called SPEF format, standard parasitic extraction format. It's an IEEE format. We'll be deep diving into the SPEF format and trying to look how can we represent the resistance and capacitance of a net in a different file. So let's try to look into all those in the next video. Thank you.
Hello everyone. So this would be the last section of the workshop where we complete the R of the PNR, the routing of the placement and ground flow. So till now we have done till CTS. So the last lecture was analysis on the post CTS, timing analysis for a typical con. So I have opened, if you see on the screen, I have opened I have invoked the Docker to run the OpenLane. So this is the next day, the day after I have run the CTS. So if you concentrate on the command which I have used in both the two, I think I have mentioned this before. So after invoking the Docker from the OpenLane, I initiated the flow.tcl for interactive run. I imported the packages, and then I did this. So prep design minus tag, the name of the folder where we have been doing the experiments till now. And if you want the configurations from the last run without overwriting a new configurations, you have to do like this: prep design, the design name, minus tag, and the name of the folder where you're doing experiment. Say for example, you want in the fresh run which you want to run, you don't want to change the tag name. That is, you don't want to create a new folder, but you want to include new configurations in the config.tcl. So in that case, you have to include a minus overwrite option along with this. So if you see here, there is hyphen overwrite option. So in that case, prep minus design echo rb minus tag the name of the folder and hyphen overwrite. So that will actually pick the new configurations value which are actually written in the config.tcl. So in this case, I have not included any new configurations. I just want the configurations which I had run in the previous flow to be taken into account in this flow. So one thing to note is that how do I know that which was the last stage that got completed. So I had run the CTS flow yesterday. So if I am to run the following stages, how will I know that which was the last run that was run in the previous flow? So if you remember, I had mentioned about the current def in the last flow. So the current def actually after a stage gets completed, the current def updates to the value, the new updated value post that run. So what I mean is that CTS has completed till now. So the current def value will be that of CTS. That will give an indication that CTS run was the last run which was done. So we'll do one thing. We'll do an echo $colon env current def. So this should be CTS def. Yeah. So this was the last run which would happen for CTS. So now the next we would be doing routing. So pre-routing, if you remember, we still have not completed the power distribution, the power and the ground rails. So that actually has to be part of the floor plan, but because of the adjustments in the open lane, this we run after CTS. So to run the PDN, power distribution network, all you have to do is type gen underscore PDN. So PDN. So this is the proc which we are using now. So this is generating the distribution network. So what all will be created is, you will see it towards the end. Actually it completes really fast. So it has read the left, it will read the def, that is the CTS def. Then it will create the grid and the straps for the power and the ground. So if you remember, for the standard cells, the standard cells are actually placed in the standard cell rows. So for the standard cell rows, we would need to have the power and the ground lines along the side rows where standard cells are fixed. So that was what it is. The first sentence, if you see, the standard cell rails. So this rails are actually providing the power and the ground for the standard cells, which are placed along the standard cell rows. So this so layer 1 is used, width is 0.48 and pitch is 2.72. So this is the reason why we would have wanted, if you remember the third lecture, if I'm not wrong, I think third or the fourth lecture, where we had plugged in our custom inverter, and I had wanted the height of the inverter to be 2.72. So this is the reason why the height of the inverter was needed to be in multiples of the site height 2.72. So if you have the height of the standard cell in the multiples of 2.72, will your power and the ground pins in the standard cell match with that of the standard cell rail power lines. So what I mean is that I'll show you with the diagram. So what I mean is this is your standard cell rows, so which are spaced at 2.72 microns. I hope you can see what I mean. So this is the standard cell rows. So the standard cell needs to be placed inside these rows, and the standard cell rows are spaced at at 2.72. That is the height of the standard cells. So we have actually laid the standard cell rails along the top and the bottom at a distance of 2.72. So if you want to place your standard cell here, I'm placing, so this was my inverter which I had designed. So I would want my power and the ground rails of this, so say this is VDD, this is VDD, and this is ground of the standard cell row. So if you want your cell, that is the inverter cell, to get the VDD and the ground, so it should ensure that the height of the standard cell should be same as this 2.72 or in the multiples of 2.72, so that this cell gets the power and the ground. Else there will be no way to provide power and ground to your cell. So this is the reason why we had wanted the height of the standard cell to be 2.72 or in the multiples of 2.72. Hope I could get that clear. So that actually explains the standard cell rails. Now then we have to provide straps for power along the throughout the chip. So thing is that what we have is a chip, a PicoRB chip, and it has to get the power. So it actually will get the powers from the VDD and the ground pads. So from the pads, this power actually goes to the straps, and from the straps it drills down to the standard cell rails. So let me see if I have a diagram which explains this, so that would be easy to visualize. So I have this diagram right now in front of me. So if you just look at this diagram and just see this, the green box which you see is, say, your PicoRB, and then the yellow boxes which you see on the tops, for example, consider the red and the blue ones also part of yellow. So these are actually the IO pads and the ground and power pads, and the square ones which you see are the corners. As the name goes, it is the corner pad. So there are 4 corners and there are 4 corner pads corresponding to each corner. Now focus on this red ones. So this red pad is the power pad, and the blue pad is the ground pad. So the power into the chip is actually coming into this pads, and from the pads the power gets supplied to this ring. And similarly, if you see, so the cross where you see, the cross which you see is actually the via that is connecting the pads to the ring. Similarly, for the ground we have an inner ring. So now the power is about to can reach the ring from the pads. Now we need to ensure that the power reaches from the ring into the chip. So for that we have this trap. So if you see this vertical line, the red and the blue, and you see it is actually attached in the top, it is connected to the ring, the outer red ring. Ring is the one which is going along the boundaries of the inner boundary of the chip, which you see the ring, the rectangle, and the strap is, the top end of the strap is connected to the ring, as well as the bottom end is connected. Similarly for the blue, it is connected to the ring. So that means right now the power is coming into the pads. From the pads it is going into the ring to power and the ground ring, and from the ring it is now going to this vertical straps. So now the power has reached the PicoRB, the green box. Now we need to supply the powers to the standard cells. So if you see the top row, if you see this many boxes which are the rectangular boxes, so those are basically the standard cells. So if you remember, I told you the standard cells are actually placed in the central rows, and this is the You can see the arrow mark here, standard cell row. And we need to now supply the power from the vertical straps to the standard cell rails. So you can see there is this cross here. So this is connecting the straps to the rails. Now similarly, if you have a macro in your design, this is how the power goes to the macros. But in our case, we don't have a macro. We have a completely standard cell based design. So this is how macro connection happens. So this diagram actually gives a picture how the power comes from outside to the pad, from the pad to the ring, from the ring to the straps, from the straps to the standard cell rows. So this is how you should we are designing the power distribution network. So we have this definition for the rails. The rails are this one. You see running parallel to the standard cells. Then we have the definition for the straps. Straps are in metal 4 and in metal 5. And then we have this connection statement actually connects everything. So the crosses which we are talking about, it gets actually done here in this connect statement. So this actually generates the power distribution network. So we now, if you look at the overview, we have completed the design setup by using the prep command. We have run the floor plan by using the run floor plan command. We have done the placement of the standard cell using the run placement command. Then we did a clock tree synthesis using run CTS command, a proc. Then we generated the power distribution network. Now the only thing that remains now is routing. So, and for reference, let's just see what the current def is. Let's see if this power generation did affect the def. So now you can see now the def actually has changed from the CTS one to a floor plan PDN.def. So this PDN.def actually has everything. That is the CTS def plus the power rates. Now the last thing that remains is routing. So, and for reference, let's just see what the current def is. Let's see if this power generation did affect the def. So now you can see now the def actually has changed from the CTS one to a floor plan PDN.def. So this PDN.def actually has everything. That is the CTS def plus the power rates. Now the last thing that remains is routing. So to run routing, all you have to do is run underscore routing. But before I press enter, I will show you one thing, like which all just like we did for every phase, which all switches are available for routing. So if you go to configuration and when you do less of the readme, for routing we have few strategies. So in routing we mentioned that the first the max layer that is needed, then the global routing capacity adjustment, the L1 adjustments, L2 adjustments. We will keep all the settings as default. We would focus on routing strategy. So there are four routing strategies. Four routing strategies. Routing strategy is 0, 1, 2, 3, and 14. So 5. So if you can see here, the routing strategy specifies the optimization mode to be used in the Triton route. So Triton route is the engine that is used for the routing, and the specifying a value from 0 to 3 actually uses Triton engine 30. And if you specify the strategy value as 14, that will actually use Triton route 14. So Triton route 14 is an upgradation to Triton 30. So if you specify Triton this routing strategy as 0, that means your routing would be not so optimal, like it won't converge to a 0 DRC routing. But the good thing is, it is as if you compensate on something, you are actually gaining on something else. So you will gain on the runtime, you will gain on the memory requirements. So if for a peak for the Pico orbit design which we're using, the Triton Route 14 actually take close to 45 minutes to 1 hour to complete the full run. While for the Triton Route 13 at the routing strategy mode of 0, it takes half an hour plus less uh, memory requirements. For the purpose of this workshop, we will use the routing strategy as 0. Let's just verify that's the value. ENV routing strategy. So that is 0. That is fine. Now the routing parameters are all set. All you have to do is run routing proc. You have to invoke it. So yeah. So let the routing happen. So if you can see it is raising the def which we obtained from the last. So we will let that happen. Meanwhile, I will just shed some light on the the Triton route which you are using for the routing, which will give an idea about the different stages, different phases of the routing. So so the routing, as I told before, is using the Triton route as the routing engine. So the references which I have used for this PPT is from the two sources which you see below. So explaining about the routing, so basically in any of the routing EDA tools which we are using, both in the open source world as well as for the commercial EDA tools, the entire routing phase, the entire routing as a process is actually very complex, and the solution space is a huge. It's a huge space. So what they do typically in any VLSI industry is that they divide the entire routing process into two steps. First is the fast route, and second is the detailed route. So basically in this fast the fast route, or the what do you say global route. So in the global route, the routing region is actually divided into rectangular grid cells, and it is actually represented as a coarse 3D routing graph. So what I mean is that, so fast route is basically, you see the fast route is the engine which is used for global route. So you can view routing as global route and detailed route. The detailed route is being done by the Triton route, and the fast route is and the global route is done by the fast route. So I think I mentioned a process in here, and I mentioned the engine. So this is, the routing is divided into global route and the detailed route. The global route is done by the fast route, and the detailed route is done by the Triton route. So as I was saying, in global route, you see the image to the right, you see the entire routing region. Entire routing region is actually divided into this grid cells. So this demarcated lines which you see, these are basically grid cells. And the routing graph, so the second figure which you see is actually the 3D routing graph, which is actually used during the global routing in fast route. So the output, this fast route is followed by the detailed route. So the detailed route should ensure that that it needs to realize the segments and the VRs in accordance with the global route solution. So what I mean is that the output of this fast route or the global route is actually a route guide. So what you see in the second pic is that you see a purple box, then you see a pinkish green, and then a pink again, and you see these four dots, this A, B, C, and D. So these four dots are actually the four pins. It could be the four pins of the standard cell. So basically, if you look from a routing point of view, if this is a net, that is ABCD is a net which is connecting these four points, uh, you would in routing basically you want to connect A, B, C and D. So what does global routing or fast route does is that it will first create a routing guide. So these boxes, the boxes which you see here, the green, pink and the blue, are the routing guide which was obtained after fast route. What detailed route does? So till now there has been no connectivity, just the routing guides have been formed. In detailed route, we used some algorithm to find the best possible connectivity amongst all these points, that is A, B, C and D. So what you see in the picture now is one of the strategies. The dotted line that you see inside these boxes, it could be one of the best routing topologies which has been obtained after some optimization in the detailed route state. So things could get a little confusing, but I'll just try to I'll try my best to give the explanation and see if you can follow through. So in global route, all you need to remember is that the output is a set of routing guides for each of the nets, and in the detailed route we use that global route and then we do connectivity between the points. So that in the second pig you can actually see the first pic was a top view and the second pic was as a side view, how the detailed route tries to find the best possible path to connect between the A, B, C, D pins. So this was the broad classification. These are few of the features of the Triton route. So if you remember, I told you the Triton route is the engine which is used for detailed routing. The fast route, the global route is being performed by the fast route. So the Triton route actually performs the initial detail route. So this is actually the detail routing phase which is done by the Triton route. It honors the pre-processed route guides. So if you remember from the first pick, so these are actually the pre-processed route guides. So it actually comes from the output of the fast route. So the detail route tries its maximum to route within these route guides. So see, honors the pre-processed route guides which is obtained after fast route. That is, the detailed router attempts as much as possible to route within these route guides. The third point is that it assumes that the route guide for each net satisfy the inter-guide connectivity. So what do I mean by inter-guide connectivity? I will be touching it in the next few slides. And then this, now that the detailed route has the route guides, it has to find the best possible way to make the routing connections between the different points. For that, it uses the MILP based panel routing. So I will be explaining all this bold letters which you see on the screen. So MILP is actually an algorithm. Which stands for Mixed Integer Linear Programming. I won't be going deep into this because it is actually another point of discussion. And it's actually based on MILP parallel routing scheme with intra-layer parallel, inter-layer sequential routing frame. So in this statement, I just want you to focus on the intra-layer. Intra-layer means within a layer. So say for example, you are doing routing within say metal 1 layer. So in this Triton route, using this MILP based panel routing scheme, in M1 the routing happens in parallel. So that's actually meaning of intra-layer parallel routing, and then inter-layer sequential. That means in between layers, for example M1, M2 and M3, the routing is sequential. That means the M1 routing takes place intra-layer parallel. That means M1 routing takes place in parallel Once M1 routing has completed, then only M2 routing will take place. And say, for example, there is a connectivity between M1 and M2. So when there is a connectivity between two different layers, you know there has to be a via or via, whatever you call it. So via placement won't happen when M1 routing is taking place. That means via routing won't happen when the lower layer routing is taking place. It will happen only when the upper layer routing takes place. So if you have a via between M1 and M2, the via placement will actually take place while routing of M2. So this is what it means. So it is the Triton route is based on this scheme, in which the within one layer routing takes place in parallel, and between layer routing takes place in sequential way. So the first bold sentence which we had, word which we had seen in the last uh, slide was pre-processed route guides. You see this is pre-processed route guides. So I had told you route guides are something which you obtain after uh, global route. That is the output of a fast route. Fast route is the engine. Global route is the process. Global route is done by fast route. So, okay. So the output of the fast route is a routing guide. So so what is this pre-processed route guide? So say for example, after the fast routing, the global routing, what you get is this initial route guide. So we have a connectivity between A and B, and this is how the route guides were formed. So if you refer to the legends on the right side, there is a the purple stands for metal 1 guide, and the pink stands for metal 2, pink or peach, whatever you call it. It is metal 2. And if you see the caption which is down here, you see my mouse, the preferred direction of M1 is vertical. That means M1's preferred direction is vertical. Just draw it for a better visualization. So M1's preferred direction is vertical. So if you see, this initial route guide has how many route guides? This 1, 2, 3, 4. Out of these 4 route guides, these 3 route guides, that is this, and this, they actually are all in the preferred routing direction. But this route guide is actually in the non-preferred direction. So the preferred direction of one was vertical, but this is in the non-preferred. So whenever the tool encounters this, when it sees that there is a route guide which is in the non-preferred direction, so what it will do, it will divide these non-preferred direction route into unit width. So what is the unit width? So if you remember the first slide which we had seen here, so this global cell, this one global cell is actually one unit width. So this actually the tool will divide this non-preferred direction route guide into unit width. So it has not divided. So this is called as splitting. And then it will do the second step. It will do a merging. So it will, which all edges will it merge? So the touching guides, touching orthogonal, who have the edge orthogonal to the preferred routing directions are merged. So what I mean is, just see in this the B one, the splitting one. So if you see right now, initially there were 1, 2, 3, 4 routing guides. After splitting, the routing guides are, let's change Blazor. The routing guides are 1, 2, 3, 4, 5, 6, 7. 7 routing guides. So which all routing guides will the two merge? So if you have an edge that is orthogonal to the preferred routing direction. So this one edge is here. So the direction of this edge is actually at 90 degrees to the preferred routing direction. So the tool will merge these edges, and then this edge is actually at 90 degrees to the preferred routing direction. So it will merge these two. So what you obtain is what you see in the C. So it has merged these two. And then finally the third step is the bridging. So the edges which are touching parallel to the preferred routing directions, edges which are touching parallel to the preferred routing directions are actually bridged with an additional upper layer. So finally what you see is this. So now just focus on the initial route guide and the pre-processed route guide. So in the pre-processed route guide, how it is different from the initial route guide. Just remove that. Okay, so this A and E. So if you see here, all the route guides are actually in the preferred direction. So that means I told you metal 1 guide's preferred direction is vertical, metal 2 is horizontal. So this non-preferred route guide has now been converted to the preferred route guide of metal 2. From metal 1 it has been converted to metal 2, and this is actually the preferred direction for metal 2. So all the non-preferred directions have now been converted to the preferred direction. So what is the good thing about that? So the good thing is that, say if you had this as the route guide, so this is actually the non-preferred route, and this will be in parallel with the upper routing guide, that is metal 2. So this will actually form a parallel plate capacitor with the metal 2. So this will result in formation of capacitance, and then that will degrade the signals. So you would always, that's the reason why, first of all, that's the reason why you have alternate orientations of the metal layer. That is, metal layer 1 is vertical, metal layer 2 is horizontal, then 3 will be vertical, 4 will be, that is to reduce the common capacitive area between these layers. So this is what the pre-processed routing guide actually stands for. And then next thing which we had mentioned in the first slide was inter-guide connectivity. So two guides, if you see two guides are connected if they are on the same metal layer and if they have touching edges, that means those route guides are connected. If we go back to this figure, so if you see the first diagram, if they have if they are on the same metal with touching edges, so that's obvious. If the guides are in the same layer and if they have touching edges, that means they are connected, right? That is obvious. The second is two guides are connected if they are on the neighboring metal and they have a non-zero vertically overlapped area. So this is the picture you see. The purple line that is common to metal 1 and metal 2. Though that purple box is actually the common non-zero vertically overlapped area. So that means these two guides are connected. That is metal 2 and metal 1. This guide is connected. So in that case, the tool will see that there is a non-zero overlap area between these two layers. Then it will try to put vias to connect. So this is where the via needs to be put to connect metal 1 and metal 2. And the second line says each unconnected terminal, and unconnected terminal means the pin of the standard cell, for example, should have its pin shape overlapped by the route guide. That if you see the first figure, this figure, so the dots, the black dots are actually pins of the standard cell. So that needs to be overlapped by the route guide. So which is done in this pic. If you see the purple box, that is actually metal 1 route guide, and it is purple box is actually overlapping the standard cell pins. So this is the reason why, if you remember, in our one of the initial while we were doing this custom lab, we wanted the pins to be at the intersection of the horizontal and vertical tracks. So this route guide actually has within itself many, the tracks. So this is the reason. So if you have the pins on the intersection of the vertical and the horizontal tracks, that will ensure that the pin is actually overlapped by the route guides. So this is what by inter-guide connectivity means. And then there was this fourth point, which if you remember, I had mentioned intra-layer parallel and inter-layer sequential panel routing. So let's break down this word. Intra-layer means within layer, inter-layer means between layers. Parallel sequence is obvious, and then there is something called the panel routing. So to explain that, I have this figure. So you see there are 4 layers: metal 1, metal 2, metal 3, and metal till metal n. Say, so each of these layers are actually divided into this dashed lines. I'll just zoom in a bit. Yeah. So if you see now, each of these layers, let's focus on let's say metal 2. So metal 2, the proper routing direction, in our case we have assumed it to be vertical. So that's why these dashed lines are actually vertical. So these dashed lines are nothing but these are called panels. And each of these panels have, and each routing guide is assigned to one panel. And if you see here in this pic, you have this blue arrows in the not the alternate, but say for example, if this is the 0th index, so this is the 2nd index. So right now the routing is happening in all the even indexes. So this is what it means by intra-layer parallel panel routing. So first the routing will happen in parallel in all the say even index panels, and then it will happen in all the odd index panels. But it is happening in parallel for a particular layer. But the routing within the layers, that means interlayer, just we try to visualize it. Routing in a layer is happening in parallel, but routing within the layers, that means from M1 to M2, will happen in sequence. That means if you see from this figure, let's draw our attention to the second figure. Now if you see the arrows now have been grayed, that means routing in M1 has completed, routing in M2 has completed, routing in M3 has begun now. So routing in M3 will begin only if routing in M1 and M2 have completed. That's a sequential execution. And if you see Mn, nothing, the routing has nothing has been done. So only if M3 gets completed will the upper layers be completed. So this is what it means. So right now, what all did we discuss? We discussed the features of the Triton route. We discussed what is a pre-processed route. What is the pre-processed route must abide to the inter-guide connectivity principle. And then we saw what is an intra-layer parallel and inter-layer sequential panel routing. For the Triton route, when the detailed route is happening, so these are the inputs. It needs to have the left file, it needs to have the depth file, it needs to have the pre-processed route guides as the input. As the output, this is what you get. You will get a detailed routing solution with optimized wire length and via count. And what are the constraints? First constraint is that the detailed route must happen within the route guide. And then there is this connectivity constraints, which we will just touch it. And then it must abide to the design rules. That means there should be no design rule violations. So these are the constraints. So I'll just give you a second or two to just see. So pre-processed guides are what you get after global routing by the fast route, and that is one of the inputs. And the constraint is that the detailed route that happens, it should be within the route guide, and it should abide by the connectivity constraints. It should abide by the design rules. So now that being said, now we have defined the space in which your detailed routing should take place. So how does the Triton route handle the connectivity portion? So that is where two concepts come into picture, the access point and the access point cluster. So if you read here, the access point is on grid point on the metal layer of the route guide and is used to connect to lower layer segments, upper layer segments, pins or ports. An access point is nothing but actually a union of all access points derived from a particular segment. So what I mean by this complex statement is I will again zoom in. Yeah, so I would like to focus just to be on this A figure. So the purple box which you see is actually rectangular box which you see is a route guide defined on metal one, which is in its preferred direction, and the peach color box is what you see is for metal 2, which in its preferred route direction, and the dashed lines which you see are the tracks that are assigned to the respective metal layer. So in this case, the dashed lines are actually the routing tracks for metal 2, and the solid line which you see in the purple box is actually the routing which has been done, which has been completed for metal 1. So if you remember, I had told you that it's a interlayer, it's a sequential routing, that only and only if the lower layer routing has been completed will the upper layer routing take place. So basically in this example, that is in the A, we are trying to connect two guides. So if you remember, how do we do it? Is we connect two guides by using vias. So thing is, so now the problem statement is where do you connect the via? So that's where the second picture comes into see. So you have a routing till this routing in metal layer till this point, and now you have 5 points where you can connect the vias. So it could be at the intersection of the this line. So if in this picture it has just shown the 2 points at which the via can be placed. So either you can place it in the upper or you can place it here in second. I'll just highlight this with the pen. So if you can see in this pic, this is one point where the connectivity where you can place the via. This is the second point, and this is the third point. I think third point has already been shown in the pic. There is fourth point here, the one below that, and the fifth point here. So yeah, so I hope you can see this. So there are actually 5 points at which the via can be placed. So all these 5 points are actually the access point. So when you have to this is the handling connectivity between the layers, and then in the second figure what you see is to connect a pin, say for example the output pin or VDD pin or ground pin of a cell within a guide. So this is the second picture, and the third picture is connecting a upper layer to a lower layer. So these are 3 scenarios, 3 connectivities which needs to be handled by the Triton route. That means connecting the lower layer with the upper layer, that is connecting the pin with in the same layer, connecting the pin of channels in the same layer, and connecting how to connect to an upper layer. So these are 3 scenarios. So hope you could get the idea of what this access point is. So all those 5 all the 5 possible points with which you can do the connection. Here in this case, if you see, there were 5 possible points where you can connect the lower layer to the upper layer. In the third pic, you can see actually there are 15 possible points. I will zoom in where can show. If I am not sure if you are able to see the picture clearly. So the horizontal dashed lines are the routing tracks for the metal 2 layer, and there are this vertical green lines which are the vertical routing tracks for the upper M3 layer. So if you see, there are actually 15 intersection points between metal 2 and metal 3. So all these points, all these possible connecting points are what you call, all these are called, each of these points are called access point, and a collection of such points are called APCs. So these 15 access points will actually come under one access point cluster. In this case, these 5 points will come under one access point cluster. In this case, 1, 2, 3, 4 plus 5. In this case also 5 points will come under one access point cluster. So I hope I was able to make you understand what access point and access point cluster is. So right now what we have the left, we have the depth, we have the pre-processed routing guides, we have the access points, like which all the possible points the connectivity can happen, and we have the access point cluster. So the objective of this MILP is, this mixed integer linear programming equation. The objective is to connect one access point to another access point optimally. So you have to find a solution that how the connections need to be made so that you connect one access point to another, and within that access point, which access point should you choose. So if you remember, there are 5 access points here in the first figure. So there are 5 places where you can actually drop vias. Yeah, you can drop vias. So first objective is to choose which access points have to be chosen. And second is, how do you make the connectivity between one access point cluster to another? Say for example, in this example, if you are connecting, if there is a connection between metal 1 to metal 3. So the metal 1 is the blue one, metal 3 is the green one. So the connection has to go through metal 2, which is the peach one. So first you need to decide how the connectivity happens between metal 1 and metal 2. Then you need to decide how the connectivity then you need to decide how the connectivity happens between metal 2 and metal 3. So basically what you're doing, you are actually connecting two APCs, two access point clusters to each other. And the goal of MILP is to find the optimal solution to connect these two APCs. So I won't go much deeper into the APC section. What I can show is this algorithm which they are used for optimized routing. So this is the algorithm, what it says. For each APC, you need to find the cost associated with each of the APCs. So for example, I have to connect an ith APC to a jth APC. I need to find the cost associated with it, and then I will do a minimum spanning tree between the APCs and the cost. So this algorithm is basically saying that I have to find the minimal and the most optimal point between two APCs. So that is actually a brief overview of the Triton route engine and the algorithm it actually uses for detailed routing. So this is actually enough said. What we will do is we will just check, just see the tool that how this processing actually takes place. So now if you can see, my routing has completed, routing stage has completed. If you see, these are the iterations which happen. So one thing which you notice here is the memory. So the memory requirement is relatively less. And then if you see at the end, you see the number of violations. So this was what I was talking about, the effort of the Triton route when you choose a higher option. For example, in this explanation, we have actually chosen the Triton route strategy as 0. So that choosing a 0 ensured didn't ensure a 0 violation. So if you use the Triton route 14, the number of final violations which you see would be 0. But the time taken would be really high and the memory utilization will also be high. The runtime will be high, memory utilization will be high. So we would have to correct these violations manually. Where do you find the violations? This is here inside this DRC. So if you do a less of this DRC file, you can actually see uh, what are the violations. So we have 3 violations which is related to metal spacing, and it is on the layer Li1. So we need to modify this manually to get rid of the violations, so that when you do a DRC, the number of violations is 0. So when now, if you check the DRCs now, it will be 3. So we will do one thing. I will just show you what I had explained a few minutes ago. First, I will show you what is the first thing which I have shown you. What's the pre-processed route guides? So in this terminal, I go for temp, cd temp, and then routing. When I do an ls, you will see something called a fast guide route. So as I had told you that routing guides are obtained as an output from global routing, and global routing is performed by fast route engine. So when you do a less, so this was what I was talking about. So these are all nets. EOI is a net, and then there is this metal 1, metal 2, this rectangles associated with it. So what you see are actually the lower left x coordinate, lower left y coordinate, upper right x coordinate, upper right y coordinate. So this was what I was talking about. This is a routing guide. So if I take the definition once more, so this is the routing guides are basically the rectangles, and these are basically rectangles which are and for a net there can be many routing guides. So if you see, this is the net, EOI is 0, and this is one routing guide on metal 2, another routing guide, another routing guides. These are our routing guides. So when you do a detailed placement, the detailed placement will ensure that the routing actually happens within these routing guides. These are defined for each net. If you see, it defined for each net. And clock was the first net. So this is a brief intro into this brief overview of the complete TNR flow. We are almost done. So what remains actually is the post route ST analysis. So now that routes have been laid, so the routes will come into picture. The parasitics associated with the routes will come into picture. So the first goal would be to extract the parasitics. So in OpenLane till now, the stuff extractor has not been included, which we have included the SPEF extractor engine along with this flow. So that will be the engine which will be used by the OpenLane team, which will be, I think, included in the further updates of OpenLane. So as of now, we will be doing the SPEF extraction outside the OpenLane, just like how we did initially how we had done the ST analysis in OpenSTA outside OpenLane. So in your machines, you need to go to the work/tool directory. So work/ and inside it you will see a SPEF extractor folder. So you enter into it, and you will see few Python files. This is a Python specific file engine, sorry. And to generate the spec, you need to specify the left and the def for the to this spec extract engine. So the format is, just watch carefully. It's a Python engine, so you need to invoke with the Python. And this is a Python 3, main.python file, and then the left file. So the left file is under tmp. This merge.left. This is the one. So do this, get the location. No need to write left read or anything. Just paste the left file. tmp/merge.left, and then space def file. Def file is the one obtained after routing. So it will be results routing. Results routing. Yeah, this is the def file. Copy everything, entire location, and I will do this step. So this will create the spec file, and the spec file will be present in the same location as that of the def. So you can see the parsing happening, the left and the def file parsing happening. Should take hardly 1 or 2 minutes to generate the spec file, and it will be generated in this location. So right now, if you see, before we had invoked that engine, this directory only had this one def file. If you see now, a new .def has been created, and in place this will be replaced by the spec file. So let's see till this. Let's wait till this gets over. Yeah. So the the spec generation arch extraction has completed. We'll check the location. The location right now is results/routing. So if you do an ls-cert here, you will see the spec file. So spec file that got created. So in our post route ST analysis, the only thing different from what we did earlier was, first you have to create a new DB, because the def has changed, and now the DB should be the routing, and the DB should have the routing, the def obtained after routing as the def. Second thing is, you need to use the Verilog file which was created pre-routing. What I mean is, if you remember, we had got a new netlist post CTS, and pre-routing actually this antenna diode insertion happens. So that means you are inserting a component into your design. That means the netlist will modify. So if you see now, this was the first one, was the one which we obtained after synthesis. Then in floor plan and placement, there was no modification to the netlist. That's why no netlist generated. In the second, we obtained a netlist after CTS, because the clock buffers were inserted in the design, so the netlist got modified. And these two netlists actually happen before the routing. In routing, the antenna diodes got inserted. So the final netlist which was used by the tool before routing was this. So in our post STA analysis, we would be using this as the read Verilog netlist. Then we would be we can use the same SDC file as the as reference. Then we need to introduce a new command, read_spec, which is actually for reading the parasitics. So that is how that's all we will be needing for the post route ST analysis. So this was the entire PNR flow and of the entire PICO-RV, and we did a hell lot of things in this workshop. We made our own design, we inserted into the PNR, and we saw the variations, we analyzed the timing, we analyzed timing at 3 phases. So you can see the importance of STA in physical and routing. Only if the timing is met do we go forward. So it's an iterative flow basically. First you focus on congestion, then you see if the congestion is apt or not. Then you move towards the timing, then you see the timing is correct or not. And finally routing, and followed by the DRC, where you clean any DRC errors. So right now in the design we have 3 DRC violations. So when you experiment, you can use the Triton 14 strategy, that is setting the routing strategy as 14 and then running the route. So you will understand what I was actually referring to. It takes longer time, but it will ensure that your design converges. That means converges means there are zero DRC errors. So hope you could learn a lot from this workshop, and I'm happy that I could be a part of it in a small way or another. So I would request you to learn a lot about OpenLane. It is actually very close to what commercial AT tools are based on. So till then, happy learning and see you again.